How's it going, accelerated chemistry students? This is going to be our notes over the nature of liquids, and we're going to consider this chapter 13, section 2. So let's talk about a model for liquids. So we just talked about model for solids in the last notes, so now let's talk about it for liquids. Gases and liquids have a key difference between them. The particles in a liquid are attracted to each other. These intermolecular attractions keep the particles in a liquid close together, which is why liquids have a definite volume. Remember, we talked about London dispersion, dipole-dipole, and hydrogen bonding as our intermolecular forces. This is what keeps liquids so close together. Liquids are much more dense than gases are. Increasing the pressure on a liquid has hardly any effect on its volume. The same is true for solids. Liquids and solids are known as condensed states of matter. Evaporation. The conversion of a liquid to a gas or a vapor is called vaporization. When this conversion occurs at the surface of a liquid that is not boiling, the process is called evaporation. Think about a puddle sitting outside on a sunny day. It doesn't boil as it disappears, it evaporates. This is happening at the surface of the liquid. The process of evaporation has a different outcome in an open system, such as a lake or a puddle or an open container, than in a closed system, such as a sealed container. If we look at the left side, we see that in an open system, molecules that evaporate can escape from the system. But in a closed system, the molecules collect as vapor above the liquid, and some end up condensing back into the liquid. During evaporation, only those molecules with a certain minimum kinetic energy can escape from the surface of the liquid. So that means that the particles are running around fast enough that they're able to escape the liquid state and get into that gaseous state. A liquid evaporates faster when it's heated. Heating the liquid increases the average kinetic energy of its particles. The added energy enables more particles to overcome the attractive forces, keeping them in the liquid state. As evaporation occurs, the particles with the highest kinetic energy tend to escape first. The particles left in the liquid have a lower average kinetic energy than the particles that have escaped. So think about if you're running around in the gym and you're trying to get out of the gym, if you're running from point A to point B, the faster runners or the faster particles are going to be able to escape and get there quicker. As evaporation takes place, the liquid's temperature decreases. Evaporation is a cooling process. You can observe the effects of evaporative cooling on hot days. When you sweat, water molecules in your perspiration absorb heat from your body and evaporate from the skin's surface. This evaporation leaves the remaining sweat that's on your skin cooler because the hotter sweat droplets or sweat particles were able to evaporate, leaving the cooler ones behind. The perspiration that remains cools you even further by absorbing more of your body heat. So now we're going to talk about vapor pressure. The evaporation of a liquid in a closed system differs from evaporation in an open system, which we saw with those containers on a few slides ago. When a partially filled container of a liquid is sealed, some of the particles at the surface of the liquid vaporize. These particles collide with the walls of the sealed container, producing pressure. A measure of the force exerted by a gas above a liquid is called vapor pressure. Over time, the number of particles entering the vapor increases, and some of the particles condense and return to the liquid state. So we can think of this equilibrium. We have liquid evaporating into a vapor or gas, and then that same vapor condensing back into a liquid. When these occur at the same rate, that's when we say that the system is in equilibrium. Eventually, the number of particles condensing will equal the number of particles vaporizing. Like I said, that is considered equilibrium. In a system at constant vapor pressure, a dynamic equilibrium exists between the vapor and the liquid. The system is in equilibrium because the rate of evaporation of the liquid equals the rate of condensation. at equilibrium. Here's sort of an informal definition. The forward and reverse processes are occurring at the same rate. So vapor pressure and temperature change. An increase in the temperature of a contained liquid increases the vapor pressure. This happens because the particles in the warmed liquid have increased kinetic energy. More of the particles will reach the minimum kinetic energy necessary to escape the surface of the liquid. In a sealed gas-liquid system at a constant temperature, eventually the rate of evaporation equals the rate of condensation. So we're going to talk about boiling point. When a liquid is heated to a temperature at which particles throughout the liquid have enough kinetic energy to vaporize, the liquid begins to boil. Bubbles of vapor form throughout the liquid, and they rise to the surface and escape into the air. The boiling point is the temperature at which the vapor pressure of the liquid is just equal to the external pressure on the liquid. So what that means is those vapor particles are pushing against the atmospheric pressure at about the same force, and that's what causes liquids to boil. A liquid boils when its vapor pressure is equal to the external pressure, and liquids don't always boil at the same temperature. Because atmospheric pressure is lower at higher altitudes, boiling points decrease at higher altitudes. So if we look here at sea level on the left, we have 101.3 kilopascals as our atmospheric pressure, and we are at 70 degrees Celsius, and we don't see any boiling. If we go to the center photo, we have sea level. We're still at sea level, and we have the same force pushing down, 101.3 kilopascals, but we're at 100 degrees Celsius, and we can see that there are vapor bubbles forming inside that liquid. So we would say that this liquid is boiling. Now, if we go over to on top of Mount Everest, we're up so high that the atmospheric pressure is only 34 kilopascals. And we can see our temperature is at 70 degrees Celsius, and we're boiling. So since there's less atmospheric pressure, the vapor pressure can be overcome a lot sooner or at a lot lower pressure, causing these to boil at a lower temperature. So vapor pressure versus temperature. You can use this graph to show how the boiling point of a liquid is related to the vapor pressure. At a lower external pressure, so we have pressure along the y-axis, temperature along the x-axis. At the lower external pressure, the boiling points decrease. And at a higher external pressure, we see that the boiling points increase. Boiling is a cooling process similar to evaporation because the gases and the vapors require more energy, and the liquid is given off the higher energy particles. The vapor produced is at the same temperature as that of the boiling liquid. And then we have the normal boiling point, and that's defined as the boiling point of a liquid at a pressure of standard pressure, which in this case we're going to say is 101.3 kPa. So over here on the right, these are just some normal boiling points for some of these liquids at standard pressure. All right, so in review, the interplay between the disruptive motions of particles in a liquid and the attractions among the particles determines the physical properties of a liquid. So depending how they interact, that affects their boiling points, how they're going to evaporate, and their vapor pressures. During evaporation, only those molecules with a certain minimum kinetic energy can escape from the surface of the liquid. In a system at constant vapor pressure, a dynamic equilibrium exists between the vapor and the liquid, and the rates of evaporation and condensation are equal, or they're in equilibrium. At a temperature at which particles throughout a liquid have enough kinetic energy to vaporize, the liquid will begin to boil. And lastly, liquids with stronger IMFs will evaporate slower and have higher boiling points. As always, all the information on these slides has come from Pearson Chemistry, and it has been acquired and adapted from Pearson Chemistry 2012 edition of the textbook, the resources CD, and pearsonchem.com. Have a good rest of your day, guys.